Hello everyone, and welcome to week 11 of the Intro to Robotics course. And so we're going to continue looking at the CS aspects of the course. So far, we have been looking at recursive state estimation, and we talked about various assumptions we make on the belief model, the motion model, and so on and so forth, and derived different classes of filters, right? So this week we will look at certain other components that we need to allow us to implement these algorithms that we discussed, right? So we need to really look at how we are going to come up with the motion models, right? And how we are going to come up with measurement models, and as well as a notion of a map, right? That gives us the specifications of the environment in which we expect the robot to operate in, right? So the motion models give us, if you remember, the probability of xt given xt minus 1 and ut, right, where xt minus 1 is the state at time t minus 1 and ut is the action that you performed at time t, and xt is the resulting state, right. And so this is the model that we use in the prediction step of the filter algorithms, right. And then the next thing is the measurement model that tells you what is the probability that I will make a specific measurement zt given that I am in state xt. So remember that xt and zt and even ut can be vectors, right? They are not necessarily scalars, even though many of the illustrations that we saw were all with scalar quantities, just to make the presentation easier, right? And again, maps, like you can see here, a sample here, or some kind of a representation of the robot's environment, and that we will use in the reasoning of the filtering step, and as we will see later in terms of planning, right, motion planning, and trying to decide how to get from point A to point B in a particular environment, right. So we'll then be using the notion of a map, and most of the maps that we will be looking at are what are 2D maps, right. I mean, looking mostly at the two-dimensional projection of the workspace and not necessarily 3D maps, and these are usually sufficient for motion planning, right, and some forms of localization that we will talk about later, right. But then you could have more complex maps as well, depending on how complicated your workspace is, right. Okay. So what I'm going to do is first talk to you about certain kinds of motion models. Okay. Next, we'll talk about maps, right, and then we'll go on to talking about measurement models, and which again, as we have done in the filtering case also, I'll be talking about very specific examples, but then depending on what your application is, you might want to use more or less complicated model, and that you will have to pick up as you go along. Okay. So the first thing I'm going to talk about are what are called velocity motion models, right. A velocity motion model assumes the following, right. So I'm going to assume that my robot state is described by some position, right. It could be the x coordinate, the y coordinate of the robot, and some kind of an orientation theta, right. So this is a standard 2D robot location and pose representation, right. And I'm going to assume that the control to this robot is given through rotational and translational velocities, right. So we could think of control as being specified through a multitude of methods, right. It could be through torques to motors, it could be through final displacements, or like we see here, it could be through the velocities that result from the controls that we apply, right, from the changes to the drives and so on and so forth. What is the resulting velocity, right. So I'm just going to assume that you have the translational velocity Vt, and you also have the rotational velocity omega t, and this constitute your action at time t, right. And the convention we'll assume, even though we are not going to delve into it too much, so positive rotational velocities induce a counterclockwise rotation, and negative rotational velocities induce a clockwise rotation, right. So clockwise would be this, counterclockwise would be like that, right. Counterclockwise would be like this, clockwise would be like this, right. And positive translation velocity Vt, as is normal, correspond to forward motion, and whichever is the direction orientation that the robot is facing in, it will move forward along that line. Okay, so that's what the forward motion here means, right. And so what we will do now is look for some kind of a closed form algorithm, right, for computing the probability p of xt given ut and xt minus 1. Okay. So this is really what we want, right? This is what the motion model is, the probability of xt given ut and xt minus 1, right? So this algorithm is going to accept as input an initial pose, right, which is given by x, y and theta, right, and a control ut which we will denote by v and omega, right, and a potential successor state xt which is given by x prime, y prime and theta prime. So given all these three, this algorithm will return a probability that x prime, y prime, theta prime is a resulting state by applying actions v and omega in state x, y and theta. Is that clear? So the resulting state xt is x prime, y prime, theta prime, and so what this algorithm is going to compute is, hey, how likely is it that if I start from x, y and theta and apply v and omega to the robot, I will end up with x prime, y prime, theta prime as my state. What is the probability that will happen, right? So that is basically what this algorithm is computing, right? So right, and the other thing that we are going to assume is the difference between t minus 1 to t is always a fixed duration delta t, regardless of whether it is 1 to 2 or 15 to 16, right? Whatever is the time step, we are going to assume it's of a fixed duration delta t, and this allows us to make the model a little simpler. Okay. So normally we would have seen this kind of forward kinematics model in terms of deterministic dynamics, right? Given a xt minus 1 and a ut, you know what xt will be, right? You solve some differential equations and you find that out. But what we are doing here is trying to make this into a probabilistic model to account for all kinds of non-determinism that is there in a real system, right? And this allows us to then directly plug into the filters that we have seen in the previous weeks, right? So here is the algorithm. This looks a little complicated, right? So I'm going to actually walk you through this, right, slowly. Okay. So before that, I just wanted to point out one thing, right? So if I have initial pose x, y, theta, and I move in a constant velocity of v and omega throughout the duration delta t, so we are assuming that we start from the location x, y and a specific pose theta, and we are going to move with a constant translational and rotational velocity over a duration delta t. So what is that going to mean? It means that we will be moving in an arc of a circle, right, that's going to be centered at some point, right? So let's say that you have so I'm going to be moving in a circle, right, with some center, right, given by say some coordinate x star, y star, right, and then I'll be marking out some segment of the circle over which I will move, right? So I start here, then I end here, and my orientation here is some theta, and my orientation here could be some other theta. Okay, so the robot could start here and it will end there, and it's starting with some orientation which is theta here, and the orientation there is theta prime. So because I'm moving with this constant velocity, I'll be describing some arc of a circle with some center, right? So this is essentially what we will be looking at, right? And so this is what this algorithm also captures right now. So what we have to first find out is what is the center of the circle that I am going to tend, right? But notice that this whole idea of moving along this along a circle, right, is fine as long as I have no noise in the world, right? If I have some kind of noise, then this is not going to be exactly the motion that I'm going to execute, right? So we'll have to figure out what will be the actual motion that I'll execute as well, right? So what I'm going to do right now is going to assume that, right? So given that x and x prime, right, where the starting x coordinate and the ending x coordinate of the motion, and y prime are the starting y coordinate and the ending y coordinate of the motion, and theta was the orientation that I was originally facing, right, theta was the orientation that I was originally facing. So remember that my forward movement would be along the direction theta. So the center of the circle, right, that I will be following is given by x star and y star as this equation, right. So you can actually look at the book to figure out how we arrived at this expression, but this is essentially like saying that, okay, I am starting at x comma y and I am ending at x prime comma y prime, right. So a perpendicular drawn at the midpoint of these 2 points, right, a perpendicular line drawn at the midpoint of these 2 points should go through the center of the circle, right. So that's essentially the idea here, right. So that is where we come up with. So x star and y star are essentially trying to figure out what should be the midpoint of the circle, assuming that x and that x y is the starting point and x prime y prime is the ending point, and I'm having an angle theta to start with. Okay, so this is essentially what I have, and solving for this equation, I get mu is given by this expression, right, and so I compute mu first and then I plug that in here to find what my x star and y star is, and the distance I am from x star and y star when I start basically, or when I end, I mean you could use either one of these, should give me the radius of the circle that I am traversing, right. And likewise the angle that is subtended by xy and x prime y prime at x star y star gives me the total angle that I have traversed from my beginning, right. Now given that, so this is the total angle I have traversed, right, I can compute what my v hat and omega hat. So what are v hat and omega hat? These are the actual velocities that I traveled with, right. So what is v and omega that is given as part of ut? The v and omega that is given as part of ut are the actual velocities that I applied to the robot, right. Due to a variety of noise parameters in the world, the robot actually travels at v hat and omega hat. And how do I get this v hat and omega hat? This is basically the rate at which my angle changes times the radius. So this basically gives me the distance I have traveled, right, and delta t. So r star into delta theta gives me the distance I traveled, and delta t is the time I took, right. So this is basically the actual velocity of travel, and this delta theta is the angle that I have traversed according to this, and delta t is the time I took, and therefore omega hat is the actual angular velocity that I have. Okay. So intuitively I hope it makes sense. So this x star y star is the center of the circle that I am traversing when I am moving with the velocity vt and omega t, v and omega, right. That's the assumption here. I am assuming that this will be the circle that I am traversing, assuming that I have a constant velocity for the time delta t, right, constant angular velocity and translation velocity, right. And so this is the center of the circle, and this is the radius of the circle. So this is the total angle I have traversed, right, and this is the effective translational velocity and effective angular velocity. Okay. Now what is going to happen is, because I am assuming that right, so I am traveling with this constant translational and angular velocity, and my entire computation has basically assumed that I am going to end up at x prime y prime. I never looked at theta prime, right, I never looked at theta prime. Therefore this model up till line 8 does not really ensure that I end up at theta prime, right. It ensures that I end up at x prime y prime, right. It's assuming I'm ending up at x prime y prime is what it's doing the computation. It never assumes how did I end up at theta prime, right. So for that, what we do is we look at the rate at which so we look at how much angular velocity we have already accrued, right, and then we compute a correction which we call gamma prime, right. So this correction gamma prime is the correction that we make to the the effective angular velocity, so that I end up at theta prime, right, and not theta plus delta theta. Does that make sense? So theta plus delta theta is what I am right now modeling here, right. So I am saying that delta theta is the angle that I would have moved if I start off at x comma y with angle theta, right? I end up at x prime comma y prime, right? I'm assuming I would have actually my pose would have changed by delta theta, right? But because there is noise in the angular rotation also, right? I end up at some theta prime, right? Now theta prime need not necessarily be delta plus it need not necessarily be theta plus delta theta. It's an independent value that we know that's given to you as part of xt. So to account for the noise in the angular rotation, right? So we take the actual angular distance that's traversed, find out what the actual angular velocity should be, right? Subtract the number that we already computed, which is omega hat, right? And call this correction to the angular velocity as gamma hat, right? So my actual model now is my real translation velocity is v hat, right? My real angular velocity is omega hat plus gamma hat, right? But my action that I have applied is v and omega, right? So now the question that we have to really ask ourselves is, hey, if I apply v and omega, right, what is the probability that the true velocity that I see will be v hat and omega hat plus gamma hat? Okay, is it clear? So now the question, the noise question, right, the probability question becomes, okay, given that I applied v and omega, right, given that I applied v and omega as the actual actions at time t, what is the probability that the effective actions that were applied to the robot are v hat and omega hat plus gamma hat, right? So ideally I would like v hat to be equal to v and omega hat to be equal to omega, right? And omega hat to be equal to omega and gamma hat to be 0. I don't have to apply additional correction at all, right? I would really like my v hat to be v, my omega hat to be omega, and my gamma hat to be 0. So that case is the ideal noise free case, right? But then we wouldn't be here, right, if everything was ideal and noise free, and therefore we are looking at this noisy case, and we are going to model this probability that, okay, you apply v, what is the chance that the actual velocity is v hat, right? So I'm going to look at v minus, right, I'm going to look at the term v minus v hat, right, and I'm going to define a probability distribution for v minus v hat. Remember, what would I like it to be? Ideally, I would like it to be 0, right? So what this function probability is, it models some probability distribution that has a 0 mean, right, which is the most likely thing, right? So 0 mean, I would like to have it, I like it to have 0 mean and some variance given by this term, right? So we'll see in the next slide, right? So the probability function, right, so this is what we had, probability x comma b is going to tell you, okay, what is the probability that you observe x, right, when the actual distribution of x is modeled with a variable that has 0 mean and a variance of b. Okay, so that's what we are looking at, right? So if you think about the various terms that we have modeled here, right, look at the various terms we have here. So we have v minus v hat. So remember, ideally v hat should be v, therefore v minus v hat should be 0, right? So we would like this to be, this probability function to have the maximum probability at 0, but then v minus v hat will be some small number. Therefore if it is close to 0, we would like this to have a high probability. If it is very far from 0, we would like this to have a low probability, right? And how we control the width of this decay, right, width of this probability is given by this expression, which is alpha 1 v plus alpha 2 omega, right, where alpha 1 and alpha 2 are actually noise parameters that tell you how much the variation in the velocity depends on the actual magnitude of velocity both in the translational case and in the rotational case. So, as you would expect, right, naturally if you are moving very fast, okay, you will have a higher error, right, and whether it's in the angular direction or in the translational direction, right. So, whether so whichever component of the velocity it is, the faster you are, the more the error would be. And so therefore alpha 1 and alpha 2, in fact all the alphas tend to have a positive, small positive quantities, so that they model the influence of the velocity on the errors, right. So, the first term gives you, okay, what is the probability of v minus v hat occurring, right. So, we have already computed v hat, we know what v is, right, that is given to you, right. So, and so what is the probability that you will see that difference. The second term likewise does that for omega, right, and here alpha 3 and alpha 4 again are parameters that look at how the magnitude of the velocities affect the error in the angular position, right. And likewise the second the second component of the angular error, which is gamma hat, again is given by a zero mean and variance B distribution, where again B is a factor that depends both on magnitude of the translation velocity and magnitude of the rotation velocity, and you have alpha 5 and alpha 6, right. So, all the alphas are positive quantities, right, and each of these pairs of alphas determine the effect of the magnitude of the velocity on the respective errors. Okay. And so, this probability function, right, so where I am looking at the probability of x given a variance b, right. So, the mean of this distribution is always going to be 0, right. Therefore, I could model this as a Gaussian random variable. So, that gives me this expression gives me the Gaussian. As you can see, it's 0 mean, the mu is not, the mu does not figure into the expression at all. Or I could think of it as a triangular distribution, where the profile looks like an equilateral triangle, right. The profile looks like an equilateral triangle, something like this. Right, and so outside of this triangle's base, the probabilities would be 0, and within this it will basically follow this kind of a linear decay, right. So, this is basically, this would be the 0 mean part, right. That would be the 0 part where you have the highest probability, and then you have the linear decay on both sides, and outside of a certain range the probability would be 0 as indicated here. Okay. So, this is called the triangular distribution. So, you could use either the normal distribution, which is our friend, or which we have seen it multiple times in the past, or we could look at the triangular distribution. Okay. Does that make sense? So, it's a little complicated. So, a lot of things are packed into this. So, basically here we assume that there is a initial noise-free transitions, right, but the actual velocity and that's applied to it is v hat and omega hat plus gamma hat, right. And then to see that this is the actual velocity components that are applied, right. So, right, for this to be the actual velocity components that are applied, okay, what is the probability that will happen, assuming that the true velocities that we used were v and omega. So, that is basically what this function returns. Okay. So, this is one way of looking at it, where I am actually returning the probability to you, right, so here is an example. So, remember I told you alpha 1 to alpha 6 are the ones that control how much noise is there in the model, and so here are 3 different predictions made by this motion model, right, based on different values of alpha, right. So, the first figure, right, has a moderate value for alpha 1 through alpha 6, okay. It has a moderate value for alpha 1 to alpha 6. So, this is the starting position, right, that is the starting position, and that is the ending position. So, this is x, y, and that is theta, and this is x prime, y prime, and that is theta prime, right. So, and now if I look at it, so this is basically my probability distribution. So, you can see that it is spread out both in the translational sense and also in the angular sense, right? Both in the translational sense and the angular sense, this distribution is spread out. Now, when I look at the second case, here the distribution is spread out only in the translational sense, right? And the angular distribution is small. So, that means that my alpha 3, alpha 4, alpha 5 and alpha 6 are small, right? And my alpha 1 and alpha 2 have large translation. In fact, alpha 1, alpha 2 have a larger error in figure B than they do in figure A, right? And in figure C, you can see that my alpha 1, alpha 2 are small. Therefore, I have a smaller translational error, but I have a larger angular error than I had in A. So, basically my alpha 3, alpha 4, 5 and 6 would be larger in figure C, right? And alpha 1, alpha 2 would be smaller than in figure A. So, this is basically the kind of predictions that you would see for the probability distributions or for various values of alpha 1 to alpha 6, okay. So, we looked at the proper fully parameterized model in the previous example. A slightly simpler version could have been to use a particle filter, right. So, if you are trying to use a particle filter, basically, if you remember, right, so I do not really compute it in a closed form, all I do is draw samples according to the motion model, right. So, as long as I really need to only draw samples according to the motion model, instead of computing a full form distribution like I was doing earlier, for every point I query, I return a value. All I need to do is, hey, can you return 10 samples from this forward model, right, according to this distribution, right. So, basically, I need to be able to draw samples according to probability of xt given ut comma xt minus 1. If you remember, when we are talking about the particle filter, we never said anything about the motion model. All we really need is a way to draw samples from this distribution. So, what this model is going to accept, right, now what this motion model is going to accept is an initial pose like an xt minus 1 given by x, y and theta and a control v and omega, and it is going to generate a random pose xt according to this distribution, okay. Notice that we are going to make the same assumptions that we had for the previous model. What are the assumptions we had for the previous model? We are going to assume that the velocity is actually v prime, right, and v prime is given by, or v hat, and v hat is given by v, some plus some noise that is proportional to both the linear magnitude of the velocity and the magnitude of the angular velocity, right, magnitude of translational and magnitude of angular velocity. So, v might be the actual angle, that the actual action that I applied, but some other v hat and omega hat are the true velocities with which the robot is moving, right, and that true velocity distribution is what we have to be looking at when we are sampling from for the particles at xt. So, looking at the figure again, so you can see what we are going to do. So, we have your original v, right, I am going to draw a noise, because remember it's zero mean, right. So, a sample basically takes a zero mean distribution with variance of alpha 1 v plus alpha 2 omega, right. It is going to take this as the input. This is basically the variance of the distribution I am sampling from. So, I draw a sample from that distribution and that gives me my v hat. Likewise, I draw a sample from alpha 3 v plus alpha 4 omega as a variance, okay, and that added to omega gives me omega hat. Likewise, I sample a gamma hat as well, right. Now, my actual angle, right, is theta prime is given by theta plus omega hat delta t plus gamma hat delta t, and my x prime and my y prime are given by these expressions, right. This is essentially the forward model. I start from x, y facing an angle theta, right, and I move with v hat, omega hat as my velocities, and therefore I end up with x prime and y prime as my final positions, right. So, you can think of lines 2 to 4 as actually doing the stochastic part of it, which is, hey, given a v, give me a v hat, given a omega, give me a omega hat and give me a gamma hat, right. So, this is basically the stochastic part of it, right. So, I perturb the actual v and omega to get my v hat, omega hat and gamma hat, And once I get that, the actual prediction of x prime, y prime and theta prime are deterministic equations, right? Just using the kinematic motion model to get me the actual locations. And if I call this function repeatedly, I'm going to get different samples depending on what values I sample for v hat, omega hat and gamma hat. So this is basically the particle filter version of it. So this is slightly easier to implement, and it goes with the particle filter that we used for the motion tracking earlier, right? And just like what we saw earlier, right? So if I do this and if I draw say 500 particles, so this A, B and C correspond to the same alpha settings that we had in the previous figures A, B and C, and you can see here this for moderate error. So you see a moderate values of alphas, you see a moderate spread in both the angle and in the velocities. In this case, the velocity error is higher but angular error is smaller, and in this case the velocity error is smaller and the angular error is higher, and you can see the particles getting smeared out exactly the way we saw the distributions getting modeled in the previous case. Okay, so this is essentially our discussion on the velocity model for the motion model. Okay, so next one that we are going to look at is the odometry motion model.